Okay, hi grade 8. So we're looking at outcome number 2, and this is topic 2, mixing and dissolving. Okay, so a pure substance is a material that contains only one kind of particle, like the element or compound. It can exist in three phases of matter, solid, liquid, or gas. Every pure substance has its own special set of physical properties. So properties are characteristics that describe matter, like color, odor, texture, shininess, what state it's in, density, melting point, boiling point. There's lots of different properties. So matter is anything that has mass and occupies space. So paper has mass and a banana has mass, but it's not energy. Elements are pure substances. You get them from the periodic table. So iron, gold, oxygen, nitrogen, hydrogen, sodium. There's like 117 or so elements. And then a compound is a pure substance consisting of two or more different types of elements. So like water is H2O, table salt is NaCl, sugar is C6H12O6. So it's got different elements, but they're bonded together. They're not mixed. And then we went through how to classify matter. So if I told you chocolate chip cookie, it's a mixture, and you can see different parts, so it's heterogeneous. Or if I said salt water, it's a mixture, but it all looks the same, so it's homogeneous. Or if I told you copper, copper is a pure substance, but it's from the periodic table, so it's an element. Or if I told you sodium chloride is a pure substance. It's got one kind of particle in it, and it's classified as a compound because the sodium and the chlorine are bonded together. They're not mixed together. Mixture is a combination of two or more pure substances, such as each one's properties are not lost but might be hidden. When a mixture is blended so well that it looks like one and it has one set of properties, we call that homogeneous, otherwise known as solution. Solution is a homogeneous mixture made of two or more pure substances, but it looks like one. So, for example, vinegar has the acid and water, and clean air has nitrogen and oxygen and carbon dioxide and hydrogen, helium, and other gases, but it looks like one. An aqueous solution is a solution where it's dissolved in water, so like tea, Kool-Aid, salt water, example of aqueous solutions. Non-aqueous solutions are solutions that don't have water in it, so like gasoline, nail polish remover, brass, air would be a non-aqueous solution as well, right? No water in it. And then mixtures that have two or more materials that are still visible, those are called heterogeneous mixtures. Hetero means different, so a heterogeneous mixture means you can see the different parts in it. And there's a few examples of heterogeneous mixtures. We'll start with suspension. That's a heterogeneous mixture where the particles would slowly settle after you mix them. So like Italian salad dressing, right? You have to shake it to use it, but if you let it sit, it'll settle. Same thing, mud is the same thing. It would eventually settle. Vinegar and oil would settle eventually as well. And then a colloid is a heterogeneous mixture where the particles will not settle. Okay, and so like mayonnaise has this. Then particles can be dispersed for even longer if you use an emulsifying agent. So, for example, if you need to get oil and water to mix, they won't mix. But if you add some soap to it, they would mix. But not dissolve. There's a difference. Mechanical mixture is a heterogeneous mixture consisting of two or more pure substances where you can still see each of the parts. So, for example, soil and concrete, you can see the parts in it. And uh, blood, same thing. You can actually see the parts, different parts in blood. And phases is a scientific word for the separate parts of a mechanical mixture. And we already did this activity. And then making solutions. According to the particle theory, how can a substance dissolve? What makes some dissolve and not others? It's the force of attraction. So, for example, if you put oil and water together, they don't dissolve because oil is more attracted to oil than it is to water. But if you put salt and water together, it does dissolve because the salt is more attracted to the water than it is to itself. And because particles attract one another and are always moving, a solution forms when the particles mix and move around over time. And dissolving is the breaking up and forming a solution by mixing two or more materials together. And there's an example of dissolving. So this would probably be like sugar. And then you can see the sugar is more attracted to water particles. And so they go together. We looked at solute and solvent. Solute is a substance that dissolves in the solvent. So it's the one that's in lesser amounts. So for example, salt is a solute that dissolves in water. And the solvent is a substance that dissolves a solute to form a solution. So in salt water, water would be a solvent. If you look at air, air is only made of like 17% oxygen, so oxygen would be the solute, and most of air is nitrogen, 78%. So the solute is oxygen, the solvent is nitrogen. And we looked at ways to make sure that these terms stuck with us. And soluble means it's able to be dissolved in a particular solvent. And we know that water is a universal solvent. It can dissolve many, many, many things. Uh, not everything, but it is the most common solvent on our planet. And then we talked about how we don't want to clean works of art with water because the paints are water soluble. So we would find other ways or other solvents that would work that would prevent getting the paint off, but it would get off the oxidation and any oils or dirt. And then we looked at some examples of solutes and solvents. So I already did air, like in soda water, carbon dioxide is a solute, the water is the solvent. In ocean water, the salt is the solute, and then the water is the solvent. And we just finished doing a lab rate of dissolving, how fast the solute dissolves in a solvent. We can do several things to increase the rate of dissolving. One of them is agitation, otherwise known as stirring or shaking. And we looked at other things that can affect it. So stirring causes the rate of dissolving to increase because the particles find each other. Surface area, you can grind something down to a dust and it would dissolve faster because there'll be more particle area to interact with the water. Temperature, as the temperature increases, the particles move faster, so then the rate of dissolving is faster because the particles move to the solvent faster. And then pressure, we looked at pressure, it can affect the rate of dissolving of gases in a liquid. And solubility is the mass of a solute that can dissolve in a given amount of solvent to form a standard saturated solution at a given temperature. We did a lab on solubility. So it would be grams per mil at a certain temperature. And then we just finished graphing and I showed you how to do a best fit line. So in yesterday's lab, we had different data points and we did not do connected points anymore, but we made a line that represented the data best. And then on top of that, once you have this, you could actually go to 35 degrees Celsius, which we didn't do in the lab as a temperature, go up here and across, and you could see it should take about 80 seconds for it to dissolve, given constant stirring. We looked at solubility of common substances. You don't need to memorize this chart, but we did use this chart to verify our results from lab number 3. And a saturated solution is a solution in which no more solute will dissolve in a specific amount of solvent at a given temperature, right? So that means the solvent is full of particles. An unsaturated solution is a solution where more of a solute could dissolve if you added to it in the given amount of solvent and, of course, at a specific temperature. And then a supersaturated solution would be, so let's say you can dissolve a certain amount at room temperature, then you increase the temperature and you can get it to dissolve more, and then slowly let it cool, and now that solution holds more than it would if it was saturated. We call it supersaturated. And we looked at these slides which basically explain the same thing. And there is an example of a supersaturated solution. See, the supersaturated solution is here. You add a crystal, and then all of a sudden, all the extra stuff that we were able to get dissolved because we had increased in temperature and slowly cooled it, now comes out and forms this pretty cool crystal lattice. And we looked at how to read a solubility curve, right? So if you look at 40 degrees Celsius, at 40 degrees Celsius, it looks like around 240 grams of solute would dissolve in sugar, but at 40 degrees Celsius for salt, it looks like about 40 grams. So it looks like the salt is pretty close to saturated right from the start because it doesn't really dissolve much more. But sugar, you can see it hits saturation at around 475 degrees Celsius. Why don't we go past 100? Because past 100, we're now into boiling. So then we're not talking about saturated. Now, if probably at this temperature, that would be super saturated. Okay, and so if we slowly let it cool, some of the sugar might fall out of that solution. Cleaning with solvents. Insoluble means it cannot be able to be dissolved in a particular solvent. So oil is insoluble in water. And some particles are more attracted to each other than other types of particles. So oil is insoluble because it's more attracted to itself than it is to the water. We can add detergent or soap to help make the fat more attracted to the water. We can use rubbing alcohol to remove grass stains. The grass stain will be more attracted to the alcohol, and then of course then you can clean it. So that's a good tip if you have grass stains. Rubbing alcohol, rub it on, and it will help remove the grass stains. We already looked at solubility and temperature, so I don't have the gizmo. We looked at Wemyss symbols earlier. It was on your last quiz, and I gave you a handout of the Wemyss symbols, so we've already covered this. And we're doing topic 2 review questions today, and I'm going to go on into topic 3. Topic 3 talks about separating Earth's mixtures. So why separate mixtures? When separating mixtures, it's useful to know the properties of the components and how the components differ from one another. So we can separate water. Water is a solution, so filtering is not going to work. So if we want to desalinate the water, that is remove the salt from the water, we can make salt water drinkable by desalination. So there are some methods you could do. You could boil the water comes off, the salt remains, and then you just have a way to capture the water. Desalination plants do exist, but they're very expensive to run, and they use huge amounts of energy. There is the tent method where you basically take water, salt water, you put it in a container, and you put it in another container, and then you hand a tent over it. You allow the water to evaporate. It condenses on the tent, and it drips down into the other glass. And I'll show you that more in class. Well, I'll show it to you right here. There it is. So you can see. There's a tent and sunlight, and there's the impure water, and there's a clean plastic sheet. And so it evaporates, and then it condenses on the sheet, and then it comes down into collecting containers on either side. So if you ever had to purify water, that would work. We'll look at dehydration and distillation. Dehydration is the process of removing water from a solution. Can you think of examples of dehydrated products? I can. Space food is dehydrated. Probably beef jerky is also dehydrated. The process uses evaporation aided by heat. It's very simple. It's inexpensive. You can buy dehydrators as well if you wanted to make your own banana chips and get rid of the water from it. Sometimes we want the solvent, not just the solute, so distillation is a good way to separate as well. So basically, you boil it off, right? Salt water, or if you want a mixture of water and alcohol would work as well because they have different boiling points. In any case, it boils, goes up here, and then you have water, cool water going in and out, so that's your condenser, and then you can collect that at the end. I will try and set up a distillation as a demo. We don't have enough to do it as a lab. And so if you're looking at percentage of salt in some bodies of water, the Arabian Sea has 3.7%, the Red Sea has 4.1%, Great Salt Lakes have 5 to 27, the Dead Sea has 27. The Dead Sea is super cool. You can just lie down in it and you'll automatically float. You don't have to do anything to it just because the density of it is so high, or the percentage salt in it, which makes it have a high density. In processing petroleum, we're pumping petroleum up, brings up crude petroleum that has to be processed to be usable. I mean, that would be a mechanical mixture. The process that yields the different petroleum products is called fractional distillation. In this case, distillation is used to separate a liquid-liquid solution. It's heated, and one part turns into gas, and that part vaporizes, travels up and away, and it's condensed in another chamber, and you can get oil and natural gas and other things in this separation process. Eventually, all the parts vaporize and recondense in separate chambers. Because petroleum is a mixture of different particles, they have different properties. In this case, boiling point, we can use that to separate them. So you can see, you just heat it up, and then it'll boil at different points, and then you can collect the different portions of crude oil. And then we're going to do this assignment and the topic 1 to 3 review on page 39, and that is the end of outcome 2.